Hello. In the first part of this lesson, we discussed the basic concepts of natural radioactivity. In this lesson, we will develop a basic idea of the theory of radioactivity. What is the theory of radioactivity based on? Well, you know that radioactivity is a spontaneous process. In other words, it's random. We do not know whether a radioactive atom will disintegrate now or not. For example, if I have a certain mass of radioactive element, here I have 500 grams of a material. Well, this is not radioactive. But suppose this is radioactive. Now, do you think that all of the atoms in this will all at once disintegrate at the same time? No, it doesn't happen. It's a random process. We do not know whether atom A will disintegrate now or not. It might or it might not. Now, but one thing we can be sure, that the rate at which the disintegration proceeds in a sample like this depends on the total number of radioactive atoms present in here. For example, if there are 1 million atoms in this or nuclei in this, suppose 100 of them disintegrate in 1 second. If you take a sample with 2 million radioactive atoms, then 200 will disintegrate in 1 second. In other words, we can say the rate of decay or the rate of disintegration depends on the number of radioactive atoms present in this sample. Now, suppose at any time the number present in the sample is represented by n. Then the rate of decay is actually dn divided by dt, the rate at which that n changes. Now, n changes to what? Remember, when an atom of an element X, this is an element X, emits a radiation like an alpha, the remaining atom will not belong to that element X, but it will belong to an element Y. The original element is called the parent element. So the element X we're going to call the parent element, and the element Y, which is the result of element X emitting a radiation, is going to be called the daughter element. That means as disintegration proceeds, there will be parent atoms and daughter atoms present in the same sample. Right? So, we said the rate of disintegration depends on the number of atoms originally present. Now, how do we write that mathematically? We would say dn by dt is directly proportional to the number of atoms originally present. That is the mathematical representation for that. Now, can you change this proportionality to an equal sign? Yes, I'm going to change that and write dn over dt equal to, when I replace the proportionality by an equal sign, I need to add a constant. Alright, tell me what this means. Negative lambda times n, where this lambda is a constant. Why is the negative sign? Negative sign because as time goes on, this n will decrease. The number of originally present atoms of X will decrease. So dn by dt is negative lambda n. Now this is a differential equation. If you have done a course in differential equation, or you don't really have to do a course in differential equation to solve this. Your calculus 2 will allow you to solve this. Even calculus 1 will allow you to solve this. Now, how do you solve this? We solve this by a method called the separation of variables. Now, n is a variable. With time, n changes. And t is also a variable. In solving this, we will keep one variable on the left side and the other on the right side. So look at the way I'm going to write it. I'm going to say dn divided by n, so divide both sides by n and multiply by dt, you get negative lambda dt. Well, now to solve this, solving means we've got to get an expression for n. How does n, the number of radioactive atoms present, change with time? So that is what solving means. What do? I integrate the left-hand side and integrate the right-hand side. Alright, so I would say integral dn, well, let me write that n properly. Integral dn divided by n equal to integral negative lambda dt. And of course, on the right side, the lambda is a constant, so I can write it like this. On the right side, I have negative lambda comes out, and you have integral dt. Alright, tell me, what is integral of dn over n equal to? It's a very standard integral, right? The integral of dn over n is ln n. So integral on the left side will give you ln n. And what is integral on the right side? Negative lambda times integrating dt will give you t. So that will be negative lambda t. Of course, we need to add the constant of integration. Now, the question is, we need to find an identity for that. What is that integral constant? And that can be found by using what is called a boundary condition. What is a boundary condition? Do you know anything about this n at a known time t? Do you know? Suppose we say, when you start looking at it, initially means when this t equal to 0. When this t equal to 0, you have the maximum number of radioactive elements in here. And we would say, when t equal to 0, our n equal to n0. That is the maximum number that we start with. With time, that n0 will become less and less and less. And this n, of course, is the number at any given time after a certain amount of time. So, if you set t equal to 0, this n will become n0. Let's do that in the equation. That will become ln n0 equal to, t becomes 0, this term will go, equal to c. What that means is, I can replace this c on the right side by ln n0. Now that becomes, I can now write this equation as ln n equal to negative lambda t plus ln n0. Can you simplify that? We can move ln n0 to the left. It will become ln minus ln n0, or using the properties of logarithm, I can write this as ln n over n0 equal to negative lambda t. That's simple, is that right? And now, the left side is an ln term. Now, how many of you know how to change an ln term or an ln equation into an exponential equation? Well, if I tell you ln of x equal to a, what does that mean? Ln of x equal to a. You remember, ln means logarithm to the base e. The base here is e. So this actually means x equal to e to the power of a. That's the meaning of this. ln x equal to a means x equal to e to the power of a, which brings us to ln n over n0 equal to negative lambda t means n over n0 equal to e to the power negative lambda t. Well, we have very nearly solved the equation. I can now write the solution of that equation here as n equal to, n I'm going to call n of t, the number of radioactive elements present at any given time, equal to n0 e to the power n0 e to the power negative lambda t. And this is the solution of this equation, which means we have now got a theoretical background on the rate at which radioactivity proceeds in a sample. The number of radioactive atoms present at any given time is the number you start with, the initial number, times e to the power of negative lambda t, where lambda is a constant for a given material. We started that out here. This lambda is a constant for a given material. It will change from material to material. And this lambda is called the decay constant. The decay constant. All right. Well, that now leads us to something more important. Well, these are the two basic equations we talked about so far. Remember this equation? ln n over n0 equal to negative lambda t. And this led to this equation. Now, what is the meaning of half-life of a radioactive sample? Now, we said this contains N0 radioactive atoms when we started. And with time, that N0 will become smaller and smaller. The N will become smaller and smaller. A time will come when there will be exactly half of the original radioactive atoms present in here. The rest have become the daughter element. Now, the time taken to achieve that is called the half-life period of this element. So what is the definition of half-life period of an element? It is the time taken for half the number of originally present radioactive atoms to disintegrate to become the daughter element. Or it can also be defined in terms of the rate of decay. Now, suppose the rate of decay now is 100 disintegrations per second. What is the time taken for that rate to decrease by 1/2? What is the time taken for that rate to become 50 disintegrations per second? So half-life can also be defined as the time taken for the rate of decay to become half its original value. So I give you two definitions. One is half-life is the time taken by the original number of radioactive atoms to become half its value. That means N will be 1/2 of N0 in one half-life. Now we will represent half-life by the uppercase T. So after one half-life, what is the value of N over N0 after a full half-life? After one half-life, N will be 1/2 of N0, or N divided by N0 will be just 1/2. Now, if you use that in this equation, I can write ln of 1/2 equal to negative lambda t. Now, if you use a calculator and tell me what is ln of 1/2, we can then have a relation between the decay constant and this t. But look at this. I have actually some more work to do here. When this n over n0 becomes 1/2, this t is now the half-life. So I can now replace this t by the half-life period. I hope you understand. We replaced n by n0 by 1/2. Now n by n0 becomes 1/2 in one half-life period. So this t now equal to the uppercase T, which is the half-life period. So we have ln 1/2 equal to negative lambda t. And ln 1/2 is what? What is ln 1/2? Isn't it negative 0.693? Check your calculator. So ln 1/2 is negative 0.693, and that is equal to negative lambda t, where t is the half-life period and lambda is the decay constant. So I can now write lambda, the decay constant, equal to 0.693 divided by the half-life period. A very important relation. We will use that as we go on. Now, that can be used to modify this equation. How will we do that? I can now use lambda equal to 0.693 divided by the half-life period into this equation, and I can rewrite it like this. N of t, the number of disintegrating atoms at any given time, equal to n0 e to the power 0.693 over t, that is your lambda, well of course there's a negative sign, times t, and that equation is a useful equation too. Alright. Well, let's say that this is a certain mass radioactive material, and its initial mass is m0. So we start with m0 gram of radioactive materials. That means all of it is radioactive. Now, after one half-life, how much of this is still of parent X? After one half-life. After one half-life, there will be m0 divided by 2, or 1/2 of m0 will still be the parent X. The rest will be daughter Y. Well, so this is after one half-life. Let's say after one half-life. Tell me, after another half-life, how much of the original material is left? After another half-life, only half of this will be left, isn't it? So half of this will be 1/4 of m0. So that is after two half-lives. Well, how much of the original material is left after another half-life? After another half-life, only one-half of this, which will be 1/8 of m0 after three half-lives. So after one half-life, 1/2 of m0 is left. After another half-life, only 1/4 of m0 is left. After another half-life, that means after three half-lives, only 1/8 of the original material, original radioactive material is left. What happened to the rest? That rest became the daughter element. Now, can we write a general expression for this? After n half-lives, how much of the original material is left? In other words, I can say mn equal to that is the mass of original radioactive materials left after n half-lives, equal to 1/2 to the power of n times m0. Is that right? If you look here, this is 1/2 to the power of 1 after 1 half-lives. This is 1/2 to the power of 2 after 2 half-lives. This is 1/2 to the power of 3 after 3 half-lives. So the amount of radioactive material left in the sample after n half-lives will be 1/2 to the power of n times m0. Now, the same equation can be written in terms of the rate of decay. The rate of decay, if I call it R, if R is the rate of decay after n half-lives will be 1/2 to the power of n times R0, which is the initial rate of decay. Well, both these actually mean the same thing. Now, let me illustrate that by drawing a diagram for you now. We can represent the rate of decay like this graphically. When time t equal to 0, you started with an amount of radioactive materials we call A0. After 1 half-life, 1/2 of A0 is left. After another half-life, only 1/4 of A0 is left. After 3 half-lives, only 1/8 of A0 is left. After 4 half-lives, only 1/16 of the original material is left. And after 5 half-lives, you have 1/32 of the original material left. Well, we talked about all this in detail. And we also found these equations. Rn, the rate of decay after n half-lives, is 1/2 to the power of n times R0, the initial decay. Or the same equation, An equal to 1/2 to the power of n times A0. Well, we can now use these to solve simple problems. The half-life of xenon 54-133. This is an isotope of the element xenon. You know where that is in the periodic table? It's one of the noble gases. If you look at the noble gases, helium, neon, argon, krypton, xenon, and radon. So that is a radioactive isotope of that noble gas, xenon. Its half-life is 5 days. If we start with 1 kilogram of this isotope, how much of the original nuclei are left after 15 days? Well, to do this, first of all, you need to figure out 15 days constitute how many half-lives? 1 half-life is 5 days. That means 15 days constitute 3 half-lives, isn't it? There you are. So since there are 3 half-lives in 3 5s in 15, there are 3 half-lives in 15 days. Now, you have An equal to 1/2 to the power of n A0. And therefore, we say An, in this case, we need to find how much of the original material is left after 3 half-lives. We have An is 1/2 to the power of 3 times the original amount is 1 kilogram. Is that right? So how much is left after 3 half-lives? That will be 1/8 of a kilogram. So we start with 1 kilogram. After 1 half-life, 1/2 of that 1 kilogram is left. After 2 half-lives, 1/2 of 1/2, 1/4 of that is left. After 3 half-lives, you have 1/8 of a kilogram left. Okay, another example. The half-life of iodine-131, another isotope of iodine. At a certain time, the amount of I-31 is 4 times 10 to the 14 nuclei in a patient's thyroid. Now, what is the rate of activity at this time? How many of the I-31 nuclei remain after 1 day? Well, it's not very different from the problem we did already. The decay constant is lambda equal to 0.693 divided by the half-life. This is the relation we established in the beginning. So that will be very useful. And in this case, we know the half-life. Is that right? The half-life of iodine is 8 days. So we know that. And therefore we can find the decay constant. So that gives you the decay constant is 0.693 divided by the half-life is 8 days. 8 days in seconds. You need to represent that in seconds. 8 times 24 times 60 times 60. And that gives you the decay constant is 1 time 10 to the -6 per second. Right. So many disintegrations happening per second. Now, delta n by delta t is negative lambda n. The rate of decay is proportional to the original number, or dn by dt. Now, that will be, we know the value of lambda and we know the value of n. Is that right? We've got 4 times 10 to the 14 nuclei is contained in a patient's thyroid at a particular instant. We need to find the rate of decay at this time. So the rate of decay is delta n by delta t is negative lambda n. We have found lambda, we have the n there, and therefore at that particular instant the rate of decay is 4 times 10 to the 8 per second. There are, well, 400 million disintegrations taking place in 1 second at that time. How many of the I-31 nuclei remain after 1 day? Well, 1 day is 8.64 times 10 to the power 4 seconds. Now we have this relation. N of t is n0 e to the power negative lambda over the half-life period times t. Now we need to find the number of iodine 131 remaining after a time of 1 day. So replace this t by the number of seconds in that 1 day, and we know the half-life period, and we know n0, the original number. So use all that. The original number is 4 times 10 to the 14 e to the power of negative 0.693 times that t is 24 times 3600 divided by the half-life period is 6.9 times 10 to the 5, and that will be 3.7 times 10 to the 14 nuclei are left after 1 day. You can see basically all these equations which we discussed in the beginning can be used to solve these kind of problems. Alright, another one. A radioactive source has a half-life of 1 minute. At t equal to 0, it has a disintegration rate of 2000 becquerel. What's a becquerel? Disintegrations per second. Find the counting rate at t equal to 1 minute, t equal to 2 minutes, 3 minutes, and 10 minutes. What's the counting rate? Counting rate is the rate of disintegration. Well, is that difficult or easy? We have the relation between the rate of disintegration after n half-lives and the rate of disintegration in the beginning. Rn equal to 1/2 to the power of n R0. Now, the half-life of this sample is 1 minute. Therefore, what is the disintegration rate after one half-life? That means after 1 minute, it will be 1/2 to the power of 1 times R0, and that will be 1/2 times 2000, that is R0. So after one half-life, you have 1000 becquerel is the rate of disintegration. After two half-lives, it will be 1/2 to the power of 2 R0, that will be 500 becquerel. In fact, you can actually write the answers right from here. After 3 half-lives, the rate of disintegration will be 250 becquerel, and after 10 half-lives, it will be approximately 2 becquerels. In other words, you can see how the rate of disintegration falls exponentially, exponential decay. All right. Now, when a parent nucleus disintegrates and becomes the daughter, will the daughter be a stable element? Well, in most cases it will not be. That daughter element will also be radioactive. That means it will also follow the same rules of radioactivity. Now, this process will continue until a stable nucleus is achieved. For example, if this is radium, this is radioactive, and after it has given out an alpha particle or a beta particle, it becomes another element. That element will also be radioactive. That means it will turn into a third element. That third element may also be radioactive. After radioactivity, it will turn into a fourth element. Now, this process will continue until a stable element is achieved at the end. Now, this can be considered to be a series of activity until you reach a stable element. Now, this is actually called a radioactive series. Now, in this case, it will also decay, producing radiation. The process will continue through a series of decay until a stable nucleus is achieved. Now, all radioactive isotopes tend to emit radiations successively until the end product is a stable element. For example, uranium-92-238 decays by 5 successive emissions of alpha, followed by a beta, beta, and alpha to become a stable isotope of lead. Now, you can actually write down those equations and see how ultimately it gives rise to the stable isotope of lead. And now this is called the radioactive series of uranium, or it is called the uranium series. Now, do you want to write that down? When uranium-92-238 decays by emitting the first alpha, what is the daughter element? Can you write that down? Well, I have it here. Uranium-92-238 emits an alpha, leaving an isotope of thorium, and that isotope is thorium-234. Now, this again is alpha active. It is not stable. So this thorium-234 will emit an alpha, will become what? Well, thorium-90-234 emits an alpha, loses 2 protons, and the mass number will reduce by 4, leaving an isotope of radium, radium-88-230. Well, of course, that is radioactive. This will emit another alpha, so radium-88-230 will emit an alpha, become an isotope of radon, 86226? Well, that radon is again radioactive. It emits an alpha particle, becoming an isotope of polonium, 222. And polonium is again radioactive. It emits another alpha, and the daughter element there is an isotope of lead. But unfortunately, this isotope is not stable. You see, not all isotopes of ordinarily stable elements are stable. For example, there are isotopes of hydrogen, isotopes of oxygen that are radioactive. So this is an unstable isotope of lead, lead 218. This is beta active. So this is going to emit a beta, and what is the result? Can you write that equation? When a beta is emitted, when I say beta, I mean beta minus, a negative electron. If it is a positron, I will mention it specifically. When a beta is emitted, the atomic number increases by 1 and the mass number will remain the same. So, lead 82218 emits a negative beta, becoming an isotope of bismuth, 83, the same mass number. And this again is beta active. Can you write down that equation? Bismuth 83218 emits a negative beta, becomes another isotope of polonium. Look at this. Earlier we saw an isotope of polonium. This is another isotope of polonium. So now we have the original uranium sample emitted 5 successive alpha radiations and 2 beta radiations, and the resulting daughter is now an isotope of polonium, and polonium 218. Now this polonium is alpha active. What happens when this emits an alpha? Well, polonium 84218 emits an alpha, and the resulting daughter is a stable lead isotope. Pb 82214 is a stable isotope, whereas lead 218 is unstable. Lead 214 is a stable isotope of lead. Well, here I have an illustration of several elements and their many isotopes. Hydrogen has hydrogen 1, hydrogen 2, hydrogen 3. What are they called? Normal hydrogen, deuterium, tritium. Helium, helium 3 and helium 4. Lithium 6, lithium 7. Carbon, carbon 10, carbon 11, carbon 12, carbon 13, carbon 14. I hope you understand what they are. Now, some of these isotopes are stable, some are unstable, and unstable isotopes will disintegrate, giving rise to daughter elements that may be stable or unstable. Now, we can actually click on each of these and find out. Let's see whether each of these is stable or not. Hydrogen, normal hydrogen is stable. Deuterium is stable. How about tritium? Look at this. Tritium is radioactive. It gave rise to a beta and became helium actually. Now, how about helium 4? That is a stable isotope. Let's go and look at beryllium. That is stable, but that is unstable. It emits a beta and gave rise to beryllium 10, boron 10. Now, you can actually play with this and see if any of these stable or unstable. Carbon 12 is the normal carbon. Later on we will see that carbon 14 is radioactive. There you are. Carbon 14 emitted a beta and became nitrogen-14. You see? Now remember, carbon-14 has how many neutrons? Carbon has 6 protons and 6 neutrons when in the normal nucleus. So carbon-14 has 6 protons and 8 neutrons. How about carbon-15? That also disintegrates. If you look at the oxygen here, oxygen-16 is the normal oxygen that is stable. Oxygen-17 is also stable. Oxygen-18 is stable. Oxygen-19 is unstable. Well, you can actually play with this as you go on. Well, that brings us to an important application of radioactivity, that is carbon dating. Archaeologists, when they discover a fossil from some ancient sites, they are able to determine how old the fossil is. How many millions ago was this animal lived? Now, how are they able to find that out? We can actually use the principle of radioactivity to do that, and that is using carbon dating. We saw some time ago that carbon has many isotopes. And carbon-12, which is the normal carbon, is a stable isotope of carbon. Whereas carbon-14 is radioactive. It eventually disintegrates to become nitrogen. Now, the ratio of carbon-14 to carbon-12 in a living organism remains stable as long as you live. But when you die, what happens is the carbon-12, which is not radioactive, the amount of carbon-12 in your body will remain the same. But carbon-14, since it is radioactive, will disintegrate steadily, becoming nitrogen. So, each radioactive isotope has its own characteristic half-life. Now, carbon-12 is the most abundant form of carbon in nature, and carbon-12 is stable. Whereas carbon-14 is a radioactive form of carbon, and that decays with a half-life of 5,730 years to nitrogen-14. So that's an important information. The half-life of carbon-14 is 5,730 years. Plants and animals contain these two isotopes of carbon in the same proportion they are found in the atmosphere. So you and I and all the trees and everything around will contain the same proportion of carbon-14 and carbon-12. The ratio of carbon-14 divided by carbon-12 will be the same in you and me and the trees, and the same the ratio found in the atmosphere. When a plant or an animal dies, it ceases to take in more of radiocarbon. And therefore, the amount of carbon-14 in it will continue to decay to nitrogen-14. And since we know the half-life, we can find out how long has the decay been going on. That means we can find how long has the animal or the plant has been dead. So as carbon-12 does not change and carbon-14 continues to decay, the ratio of carbon-12 to carbon-14 at the time of discovery of a fossil will give us information about how long ago the plant or animal lived. A very important information for archaeologists. Let's see whether I can illustrate that using a problem. If a living organism has 4 grams of carbon-14 and a dead fossil of the same organism has 3.9 grams of carbon-14 now, how long has the organism been dead? Well, the original 4 grams of carbon-14 has been reduced to 3.95 grams of carbon-14. And since we know the half-life, we can now find out the time taken for that decay to take place. Well, we have n of t. I should have written A of t. The amount of carbon-14 at a given time is 3.95, and the amount in the beginning is 4 grams, and the half-life is 5,730 years. And you know the relation. N of t equal to n0 e to the power negative lambda over the half-life period multiplied by t. And so we have 3.95 equal to 4 times e to the power of negative 0.963 t divided by 5,730. Or we have 3.95 divided by 4 is e to the power of negative 0.963 t divided by 5,730. Now you probably have a question to ask me. I have left the half-life in the years and did not convert it to second. Is that okay? Yes, it is okay. If you leave the period, the half-life period in years, we are looking for this time. How long has the organism been dead? That time will also be in years. So as long as you take care of that, that should be okay. Now, in order to solve for t, we now take ln of both sides. So what do we have? Ln of this number will be ln of the right-hand side. Now, what is ln of the right-hand side? What is ln of e to the power of x? Ln of e to the power of x is x. Ln of e to the power of this quantity is that quantity itself. So that gives me ln of 3.95 divided by 4 is negative 0.01258. Check that on your calculator. Equal to ln of the right side will be this quantity, negative 0.963 t divided by 5,730. And that's a simple equation. You can solve your t from there. And that gives you t equal to 74.9 years. You see, you can calculate the number of years that organism been dead using that simple data. A very, very neat way to do that. Another example. Find the average carbon-14 activity in decays per minute per gram of natural carbon if relative concentration of carbon-14 in living organism is 1 part in 7.2 times 10 to the power of 11. Now remember, the most important ingredient in your ability to solve a problem is to understand the problem. So read that again and see whether you understand. What are the given things? We need to find the relative concentrate, but we need to find the average carbon-14 activity in decays per minute per gram of natural carbon if the relative concentration of carbon-14 in living organism is this. That means for every 7.2 times 10 to the power of 11 of normal carbon, there will be 1 carbon-14 atom. That's what it means. So what that means is carbon-14 divided by carbon-12 is 1 over 7.2 times 10 to the power of 11. For every 7.2 times 10 to the 11 carbon-12, there is 1 carbon-14. So the ratio of carbon-14 to carbon-12 is 1.4 times 10 to the negative 12. Now, we need to find the activity in decays per minute per gram of natural carbon. So we need to now deal with that 1 gram of carbon. Atomic mass of carbon is 12. And so the number of moles in 1 gram of carbon is 1/12 mole. 1/12 of 1 mole of carbon is what is in. So the number of moles in 1 gram is 1/12 mole, because atomic mass is 12 means 1 mole of carbon is 12 grams, isn't it? Your basic chemistry will tell you that. Atomic mass of carbon is 12 means 1 mole of carbon has a mass of 12 grams. Therefore, 1 gram is 1/12 of a mole. Now, the number of atoms in 1 gram of carbon, therefore, is 1/12 of the number of atoms in 1 mole. You know that the number of atoms in 1 mole of a pure substance is called the Avogadro number. Now, we talked about that earlier on in the course, in the first unit. Avogadro number is the number of atoms in a mole of a pure substance. And you know the value of that, don't you? Well, which is 6.02 times 10 to the 23. So we find the number of atoms in 1 gram of carbon, which is 1/12 of the number of atoms in 1 mole. Because 1 gram of carbon is 1/12 of a mole of carbon. So the number of atoms in that will be 1/12 of the number of atoms in 1 mole, and that is 5 times 10 to the 22 atoms. And the number of carbon-14 atoms, well, since the ratio of carbon-14 to carbon-12 is 1.4 times 10 to the negative 12, how many carbon-14 atoms are there in 1 gram of carbon? There are 5 times 10 to the 22 atoms in 1 gram of carbon. And since this is the ratio of carbon-14 to carbon-12, can you now find the number of carbon-14 in 1 gram? It will be that ratio multiplied by the number of atoms in 1 gram. So that will be 7 times 10 to the power of 10. There are 7 times 10 to the power of 10 carbon-14 atoms in 1 gram of carbon. Now, with a half-life of 5,730 years, the decay constant of lambda for carbon-14, we can now use the half-life to find the decay constant of carbon-14. You remember the relation between those two? Lambda equal to, what is the relation between lambda and the half-life? Will be 0.693 divided by the half-life. So lambda equal to 0.693 divided by the half-life. We know the half-life, therefore we can find the decay constant. 0.693 divided by the half-life in years, and write that in minutes. That will be 2.3 times 10 to the negative 10 per minute, because we are looking for activity in decays per minute. So we represent the lambda, the decay constant, in unit of per minute. Alright, so now we have the number of carbon-14 atoms is 7 times 10 to the power of 10. Its decay constant is 2.3 times 10 to the negative 10 per minute. And therefore the activity in disintegrations per minute is delta n by delta t is negative lambda n. We know the value of lambda, we know the value of n, and using those it will give you 16 disintegrations per minute per gram. So for every gram of carbon, there are 16 disintegrations of carbon-14 happening per minute. That's a good problem. I want you to look through that one more time. Another example. Radiation analysis of an old bone shows that there are an average 2 beta emissions per minute per gram of carbon in the bone. Using the results from example 5, what is the approximate age of the bone? Well, what is the result we obtained in example 5? The result we obtained is, for every gram of carbon, there are 16 disintegrations per second of the carbon-14. That's what we obtained there. Now, when we analyzed this bone, what did we find? The radiation analysis of an old bone shows that there are an average of 2 beta emissions. The activity now is 2 radiations per second. So 16, which is the original number, has been reduced to 2 radiations per second. Can we find the time taken for that reduction? Well, that is what the question is asking you, I think. Using the result from example 5, what is the approximate age of the bone? The age of the bone is the time taken for the rate of disintegration to reduce from 16 to 2. So, at the time of death, the activity of carbon-14 is 16 disintegrations per minute per gram. The present activity in the same specimen is 2 disintegrations per minute per gram. Now, therefore, we can now find how many half-lives have elapsed during this time. If n is the number of half-lives elapsed after the death, we can now write a relation. What is a relation? We have Rn equal to 1/2 to the power of n times R0. The rate of disintegration after n half-lives is 1/2 to the power of n times the original rate of disintegration. The rate of disintegration now, that means after n half-life, is given to be 2, equal to 1/2 to the power of n times the original rate of disintegration is 16. And you can calculate n from there. We have 1/2 to the power of n equal to 1/8. Is there anybody who doesn't know how to solve that equation? Solve for n from here. 1/2 to the power of n equal to 1/8. Well, gives you 2 to the power of n equal to 8, isn't it? Yes, you can simply flip the equation up. If 2 to the power of n equal to 8, what is n? N equal to 3. So the number of half-lives elapsed is 3, and each half-life is 5,730 years. Is that right? So, since one half-life is 5,730 years, the time elapsed after death is 3 times 5,730 is 17,190 years. You can see how easily we can actually judge the age of things that were dead very, very long time ago, and it is very accurate. But that really concludes our study of radioactivity, and I will recommend you go back and do all the homeworks and go through these worked examples one more time. All right? I'll see you for the next lesson later on.